Hi, my name is Cheryl Lau, and thank you for watching the recorded version of my master's thesis on perceptual allowances of anamorphic interaction cues in spatial augmented reality. So let's start off with what is arguably the most famous example of perspective anamorphosis, which is The Ambassadors by Hans Holbein the Younger. So this beautiful lifelike painting, but there's this one area that doesn't fit in with the rest of the composition. So that little smear at the bottom of the canvas is actually an anamorphic image that needs to be seen from a specific viewing angle to be understood. So if you're viewing this painting from directly in front of it, that area is going to appear skewed. However, with a slight change in viewing angle, you can see the skull in the way that it was intended to be seen by the painter. So there are actually two different types of anamorphosis. There's catoptric or mirror anamorphosis and perspective anamorphosis, like in The Ambassadors. In this presentation, we're going to be focusing on perspective anamorphosis. So later in the presentation, if I say anamorphosis, I mean perspective anamorphosis. Now, right before my thesis presentation, I actually took a trip across the world to Macau, where I saw this great example of anamorphosis in real life in a museum setting. So this is the front entrance of the Team Lab Supernature exhibit in Macau, which is filled with really cool immersive art. From most angles, this part of the exhibit just looks like unrecognizable black stripes that could be letters. However, if you step over to the entrance area right before you start lining up, you see the stripes sort of coalesce into the name of the exhibit. Now, this is just a static piece of art created using vinyl on the wall, but you can imagine how projectors could be used to change what's in that space dynamically. Later on in the presentation, I'll go over a design scenario with a spatial augmented reality museum exhibit. And here's a video showing that effect in action, because it really looks a lot better when you can see it coalesce in a video. So what's the psychology behind why we perceive images in this way? Anamorphosis relies on the viewer perceiving both the flat and the 3D versions of a given image. And some researchers have called it the integration of incompatible things, depth and flatness. So an interesting fact is that people tend to be able to tolerate different levels of distortion depending on the content of the stimulus. So for example, we're much better at undoing distortions on faces than we are on other stimuli. So this is an image from some earlier work on robustness of viewing angles on identifying rectangular boxes. So in this image, A is an example of a rectangular box, but B, C, and D are skewed. So in this study, they put these images on a flat wall and asked participants to stand at different angles to the wall. They then asked the participants to try to identify whether the image was a rectangular box or not from their viewing angle. Surprisingly, participants were very good at this until they were about 26 degrees from the wall, which tells us that people are able to correct for distortions at a pretty wide range of angles. So in Gestalt psychology, there's this idea of generic and specific viewpoints for a scene. Take the scene with hills and the sun, for example. From the viewing location indicated by that arrow, you can see both hills and the sun because most viewpoints are generic viewpoints for a given scene. Even if you change your perspective just by a little bit, you retain the same information about the contents of the scene and the relative positions. But what happens if you shift your viewing location to the left? So this is another generic viewpoint, so the image looks a little bit different, but you aren't gaining or losing a lot of scene understanding. That said, there are specific viewpoints where elements in the scene align and hide information from the viewer. So let's take a look at what happens when you shift your viewing position to this spot on the right here. At this location, objects in the scene line up in a way that hides information from the viewer. And it's very easy for this perfect alignment to go away when you shift away from this location. So this position is called the specific viewpoint. Although you would normally want to avoid showing content from these angles in design, when it comes to anamorphosis, this specific viewpoint is actually where the illusion appears. So let's go back to some examples of anamorphosis to really drive home the point of specific and generic viewpoints. The specific viewpoints in an anamorphic image is called the ocular point, and it's where you see the anamorphic effect. So here's an example of some anamorphic sidewalk chalk art at a generic viewpoint. So nothing really makes sense, and you know that you need to move to see the effect. And you can see the effect right there. Another example can be found on roads. So this warning sign isn't meant to be viewed at the generic viewpoints from the sidewalk. It's meant to be viewed on roads from where the person is driving. So the triangle really pops out and looks correct from the driver's seat. And these are both examples of foreshortening, where the stretched image produces the illusion of height at certain angles. Now, I talked a lot about the psychology behind anamorphosis, but how do we represent this geometrically? So one simplification that we can make here is that we can represent the viewer with just one point. I know that stereo vision means that we see slightly different images from both eyes, but when the stimulus is far away enough and large enough, the views are close enough where this doesn't matter. So the principle of radial occlusion tells us that 2 points look the same to an observer at point O if they are collinear or lie on the same ray with an origin at O. Anamorphosis is essentially creating an image that's meant for that ocular point O and then waiting for the viewer to find that point from somewhere else in space. If you look at the two blue areas in this image, they're actually homeomorphic because there's a one-to-one correspondence between the two surfaces in both directions. In other words, they're essentially stretched versions of each other with no discontinuities in between. So here are some examples of projections that do have discontinuities. We've been considering examples that are static and painted on the surface of the geometry so far, but Spatial Augmented Reality, or SAR for short, provides us with the option to quickly change the digital content that's being projected onto a surface. So this first example by Benko et al. Is a SAR system where the viewers can see 3D content without the use of any sort of head-mounted display. The system tracks where the person's head is and uses that as the origin point for a virtual projector. So you can see how in the first image, it sort of forms a different perspective. The discontinuities are clear, but from the viewer's perspective, it's a seamless 3D display. Another example of perspective-dependent SAR can be found in this museum guidance system that uses floor projected cues to guide viewers to the right viewing location in an exhibit. So SAR is a very cool tool, but it has some unique considerations that make it different from other immersive technologies. So first, SAR content needs to be projected onto physical surfaces. Next, projector brightness can limit its use in outdoor spaces and limit its reach in indoor spaces. And lastly, a geometric model of the environment needs to be known ahead of time to calibrate the projectors. So essentially, SAR requires a lot more detailed information about the physical space than any other immersive technologies like mobile AR or VR. Fagerholt and Lorenzen proposed a spatiality diegesis continuum that describes the user interfaces in 3D game environments where one of the axes is spatiality. Spatiality is whether or not the UI element is visualized as part of the 3D space, the way that SAR content is. The other axis is diegesis, or whether or not the UI element exists in the fictional game world. The term diegesis actually comes from Aristotle and Plato, who used it to describe a storytelling technique where a narrator tells the story to the audience. Now it's used in games to describe situations where a piece of content is part of the narrative of the game. So here are some examples of interaction cues that fit into each one of these categories. Heads-up displays are not spatial and not diegetic because they aren't part of the environment, and they're distinct from the world of the story. In contrast, a meta-representation like a health bar is part of the narrative of the game, but not part of the 3D environment of it. Geometric elements are elements that are 3D objects in the space that aren't part of the game world, like a warning message projected onto a wall. A sign along the path in a 3D game would be both spatial and diegetic. Now, that spatiality diegesis continuum was designed for 3D games, but the authors talked about how the same ideas could be extended to AR. The reality-virtuality continuum describes the continuum between the real environment and a fully virtual environment, like in fully immersive VR. So spatial augmented reality sits closer to the reality side because it relies on the physical environment around the viewer. We've already seen examples of anamorphic interaction cues in real environments, but we can also create anamorphic interaction cues using SAR. Those SAR interaction cues can then be simulated using increasing levels of virtuality. Later on in this talk, I'll actually discuss how we prototype SAR experiences using VR. Inspired by all these continuums, we propose a design space to describe anamorphic interaction cues using two different axes. Number one, the level of continuity of the projected stimulus, and number two, the need for movement. The continuity axis spans from continuous to discontinuous and describes whether the projected image is broken up regardless of the viewer's perspective. So if you think back to that homeomorphism example, that blue plane would be continuous because nothing is occluding it or otherwise creating discontinuities. Now, this is a continuous axis, even though it looks like it's binary. And we're essentially looking at how often the generic viewpoints contain discontinuities. So the other axis is the need for movement, which we separate into 4 levels for easy reference. In reality, this is also a continuous axis. So no movement needed means that the stimulus can be completely understood by the viewer without movement. And then suggested movement means that the viewer can recognize that they aren't at the ideal viewpoint, but they can still understand the stimulus. Then we have recommended movement, which is where the stimulus can be better understood with movement. Lastly, we have mandatory movement, where the stimulus cannot be understood by the observer at the current location. Now, I know that seemed like a little bit abstract, so let's walk through a design scenario that goes through all these different areas. Imagine we're at an immersive exhibit on the history of pottery. The designer of the experience incorporated anamorphic interaction cues into the exhibit to guide viewers through the exhibit without forcing them to move in any particular path or without giving any explicit movement cues. So let's take a field trip to the museum. The exhibit begins with the visitors facing a replica of the Venus of Dolní Věstonice, the oldest known ceramic artifact. So the name of the exhibit is projected on the wall above the sculpture, and it can be easily read by visitors as they enter. The name of the artifact and the decorative elements from the site of its discovery in the Czech Republic are projected all around the sculpture. And we also have a projection that highlights the crack on the sculpture from when it was assembled from 2 separate pieces. Although the information is discontinuous on different image planes, visitors are able to see the aligned image from their specific viewing location. The next part of the exhibit takes the visitors to a scene in a cave in China where some of the earliest fragments of pots have been found. To lead the visitors into the space and give more information, the designer projects information onto a flat wall at an angle where the ocular point is further into the exhibit. The angle is small enough that the viewer doesn't have to move to understand it, but they can recognize that there is a distortion that can be corrected. This part of the exhibit has a recreation of the cave wall with many fragments from clay pots embedded into the surface. Information on the contents of the wall is projected onto the cave wall. The pottery fragments cause some discontinuities in the projected image, but the information is still mostly readable to the visitors. The visitors can choose to move closer to the ocular point to resolve some of the occlusions, but they don't really affect the understanding. So this next area of the exhibit is on the invention of the pottery wheel in Mesopotamia. A model of a pottery wheel with clay on it sits at the center of the semicircular wall. The ocular point of the projection with the information on the pottery wheel is at one side of the semicircle. The image is projected at an oblique angle to the surface, and the curvature of the wall adds an additional distortion. So this indicates to the visitor that they need to go to the ocular point to undo that distortion for better understanding. One side of the pottery wheel is illuminated with the outline of a vase that's barely discernible to the visitors at their current location because it's being projected at an angle onto the pottery wheel. The pieces of the outline join to make the complete outline as the visitors move closer to the ocular point. This encourages movement to a specific location. The last part of the exhibit explores the Industrial Revolution and its effects on the pottery industry. Artifacts from a pottery factory in England are displayed along the edge of the room to guide visitors to the end of the line of artifacts, but also encourage exploration. The designer places the ocular point of a projection close to the wall at the end of the line of artifacts. This creates a long projection that's visible along the length of the wall, but is unreadable until the visitor walks to the end of the line of objects. The designer would like to end the exhibit with additional information on resources to learn more about each of the exhibits, but they want to hide this from the visitors until the very end. The designer decides to project this text onto a wall of pottery at the end of the exhibit so that visitors need to be standing at a specific location at the end to read the text. Outside of that location, the information is partially occluded and not readable. But when the visitor stands at the ocular point at the exit and look back at the wall, they see all of that information come together. All the disjoint pieces will just connect into the parting message of the exhibit. That's the participant seeing the final message. Now that was a fun pretend scenario, but would those anamorphic interaction cues actually be effective in guiding a person through a space? We designed a set of experiments that would test how well people are able to find the ocular point across different surfaces and tasks. We decided to use VR to simulate a SAR environment because it gives us better experimental control. And I'll explain how this may have affected the results later. So for this experiment on continuous stimuli, we had 12 participants with binocular vision come in for a 1-hour within subject study using a Quest 2 VR headset. This first experiment was on continuous stimuli. So we picked 4 projection surfaces that would produce continuous stimuli at most angles. So we have the flat wall as a control. Then we have the concave wall, the convex wall, and then the textured wall. So we put the participants or the projector at an oblique angle depending on the trial. In each trial, either the participant or the projector was placed at an oblique angle, which ranged from 15 to 90 degrees at 15-degree increments. So here's a diagram of the different trial configurations with what the participant sees at the top there. So on the left, we have the case where the projector is moved. The middle is where the participant is aligned with the projector. And on the right, we have the participant moving while the projector stays at that 90-degree angle. So at each of the viewing angles, participants were asked to complete 3 different tasks. The symbol recognition task is based on the Lee symbol recognition task, which is a visual acuity task that's used by optometrists. We wanted to use this task to have it correspond to suggested movement in the design space because symbol recognition is usually pretty robust against perspective distortions. The line alignment task is based on the Vernier acuity test, where patients are asked to identify whether or not 2 lines are misaligned. We took it a little bit further and asked our participants to use the joystick on their VR controller to align the 2 lines until they were one on top of another. We hope that this would correspond to recommended movement because judging alignment is difficult with perspective foreshortening at some of the angles. And lastly, we have the perfect square task. So the perfect square task is this task where we designed it to force the participants to move through the space. White squares were projected at an angle and participants were asked to move until they found the ocular point where they could see a perfect square. So here's a clip of what the perfect square task looks like from the perspective of the participant. You can see that the parts are coming together to create this perfect square. So these are the task completion times across the different surfaces and angles. You can see that there's a slight increase in completion time as the angle becomes smaller, so when they're closer to the wall. And part of this effect can be explained by the fact that there's simply more movement needed to get to the ocular point when the user is placed at an oblique angle compared to when they're already close to the ocular point. That being said, there is a big jump at 15 degrees when the projector is at an oblique angle. So this is actually really interesting because it aligns with research on the perception of boxes at different angles, the research that I mentioned earlier in this presentation. In their study, they found that 26 degrees was the point where participants where participant performance started to fall. And we're essentially seeing the same pattern here. Participants are taking longer to complete the task because it gets much more difficult at 15 degrees. Now, the accuracy for the symbol recognition task was 100% for all participants. So I'm just going to skip to the line alignment task accuracy. So in this graph, you can see how putting the projector at an oblique angle had a much larger effect on performance than moving the participant. Once again, we're seeing an increase in inaccuracy as the angle gets smaller. And this is very pronounced on the textured wall, probably because the texture on that surface warps the lines much more than any other surface in this experiment. Now, there's quite a bit of variance in the perfect square task accuracy. You can see how, once again, the participants performed worse when the projector was at an oblique angle. There wasn't much of a difference between different surfaces, but we can see an upward trend in inaccuracy as the angle gets smaller. In terms of qualitative feedback from the participants, most participants talked about how they struggled with the perfect square task. This was also reflected in the unweighted NASA TLX scores from those participants. In the post-study survey, participant 4 elaborated on how the lack of detail made it difficult to identify the location of the ocular point in the perfect square task. And this was for the flat wall. They said perfect square seemed really challenging with the most basic conditions on a flat or curved wall. It was hard to identify whether the square was actually perfect or not, since my brain would approximate what it was supposed to be. So this is some of that perspective compensation that we were talking about earlier. It's an example where robustness of perspective actually makes it more difficult to complete the task. All of the scores were below 15 out of 21 on the 21-point NASA TLX scale. So this suggests that anamorphic interaction cues don't put too much of a load on participants. The design of the second experiment was essentially the same as the previous experiment, except for the surfaces, which were discontinuous stimuli. So we wanted to cover the other half of the design space. So here are the 4 surfaces. We have the flat wall for control condition, the lightly textured wall, which creates mild discontinuities, the highly textured wall, which creates more dramatic discontinuities at different depths, and finally the occlusion wall, which completely occludes part of the image at some angles. If you think back to the previous experiment and that textured wall, the difference here is that there are more discontinuities at a wider range of viewing angles. With the discontinuous stimuli, we're seeing the same upward trend in completion time as the angle gets smaller. However, the jump at 15 degrees is less pronounced because it seems that participants were consistently able to work harder to complete the task as the angle got smaller. Surprisingly, the line alignment task accuracy was relatively consistent across all surfaces and the different configuration pairings, with the exception of the highly textured wall. So this may have been because of the combination of vertical and horizontal occlusions on the highly textured wall, because it is a little bit more complicated. Another interesting point to note is that the participants were more accurate in these trials than they were in the continuous ones in the previous experiment. So this suggests that more discontinuities actually help participants in evaluating the quality of their answers because it reduces ambiguity. The perfect square task follows much of the same patterns as it did in the continuous stimuli case, but it's slightly lower for all of these discontinuous surfaces. This is probably due to the fact that participants could use the discontinuities as clues for alignments when they were trying to figure out where to place the lines. Now, there weren't that many discernible trends in the NASA TLX responses for this experiment. In the continuous experiment, the perfect square task was more difficult for participants. But for this discontinuous experiment, it seems that the texture made all of the tasks similarly demanding. The perfect square task was still more difficult from the participant comments, but they had more clues to help them complete the tasks. So one important piece of information that we collected was the motion data for the participants during the trials. So you can see these squares with participant numbers inside of that little square at the end of a motion path. The red circle represents the starting point where the participant was placed, and the green circle represents the ocular point. There's also a green ray that represents the optimal viewing angle. The motion paths are color-coded to match the color of the square for each one of the participants. Now, there are way too many combinations, so I picked a few representative examples to use in this presentation. So here we have a comparison between behavior on different continuous surfaces for the perfect square task. The projector was placed at a 45-degree angle, and you can see how each of the surfaces led to different behaviors from the participants. As the level of discontinuity increased, it seems like the participants were better guided towards the ocular point and with more certainty. So this is a comparison between placing the projector and placing the participant at a 45-degree angle on a discontinuous wall. You can see how projecting at an oblique angle creates a lot of uncertainty and makes the participants really explore the space before getting to the answer. This is in contrast with simply moving the participants, where participants were able to discover the ocular point pretty easily and pretty confidently. This is a comparison across tasks where you can see the difference between suggested, recommended, and mandatory movement. This was on a lightly textured wall where the participants were moved. And you can see how some participants decided not to move at all for the symbol recognition task, while more of them moved closer to the target in the line alignment task. In the perfect square task, they were told to move, so that's why all of them made some sort of effort to move towards the ocular point. Given the results that we found, we came up with a set of recommendations for designers of anamorphic interaction cues. So number one is motivate movement using perspective clues. So show some of the perspective distortions to get viewers to move. Next one is encourage exploration through ambiguity. So we saw how the ambiguous continuous surfaces encourage more exploration, which is what you might want in some situations. The next one is customized for content. So some of the tasks created different movement patterns in participants, so keep that in mind when choosing the type of interaction cue to display. And the last one is obfuscate through occlusion or obliqueness. As we saw in our results and in past work, past a certain angle of obliqueness, it becomes really difficult for viewers to understand content. But you can use this in conjunction with occlusion to intentionally hide content until the viewer gets to a certain location. So one big question that you might have after all these experiments is whether or not it's even valid to mock up SAR experiences in VR. Past work by Michaela et al. Suggests that it is valid to simulate large display research in VR, but there are some trade-offs in external validity. We designed an experiment to evaluate the differences in how participants identify the ocular point between SAR and VR. This experiment has the same design as the VR experiments that I already discussed, except that there is an additional condition where everything is repeated in a SAR setup. There are some changes to make the VR and SAR conditions as similar as possible as well. So let me play a video to show what the SAR condition of this experiment would look like from the participant's perspective. So the participant's location is tracked using Vicon trackers on a hat, and keyboard inputs trigger the next trial, and also the location of the participant also is part of that. You see the keyboard input there, or when they're locking in the position that they think gives them the ocular point. There's just a second trial. Between each of the surface conditions, the experimenter would physically change the foam core surfaces and also swap out the calibration files. So there's a video of swapping out the physical board so that you can use a different surface. The same trials would be repeated in VR in the same space to make the conditions as close to the SAR condition as possible. So here you can see that I'm using a Quest Pro to get a wider field of view than with the Quest 2. And I'm using a keyboard for input to make it consistent across the VR and SAR conditions. So inside of the VR headset, the participant sees a full scale 3D scan of the room, and it's aligned to the space where they're completing the SAR condition. Now, unfortunately, we weren't actually able to run this experiment due to unforeseen hardware issues with the projector system. But we really tried to make it work. I outlined the experiment in more detail in the thesis, but we wanted to test whether there were any perceptual differences that might arise from VR simulations due to things like the fidelity of the 3D model or the field of view. I know a lot more about the projector system than I ever thought I would, and I had fun making things out of foam core, so maybe it wasn't all that bad. So in future work, in addition to actually running that experiment, it'd be interesting to explore how groups of people can interact with anamorphic interaction cues. With the participant location tracking, it would also be possible to dynamically change the ocular point depending on where the users are located. Lastly, the world of perception research is never ending, so future work could focus on different distances from the stimulus, more viewing angles, or even different cues that warp around the objects in the scene. To wrap things up, today we talked about some of the existing work on anamorphosis, SAR, and immersive interaction cues. We also presented a design space for categorizing anamorphic SAR content and walked through a design scenario. We evaluated continuous and discontinuous surfaces across viewing angles, and also proposed an experiment comparing SAR and VR. All of our findings were combined into recommendations for designers, which will hopefully help them see interaction cues from a different perspective. All right, thank you so much for listening. And if you're watching this in the future, please feel free to reach out with any questions that you might have on this work.